Hi, everybody. Welcome to Chapter 3. We're going to be looking today at the first section in Chapter 3, 3.1. It's titled The Distributive Property and Algebraic Expressions. And basically, what this is going to do is get us set up for solving equations in the future sections. So we're going to be evaluating algebraic expressions and looking at the distributive property a little more closely that we saw in Chapter 1. So let's have a look at first, before we get into the distributive property, actually, the associative property. So the associative property says that you can, if you have a multiplication problem like this, that you can essentially, because it is really, this is the equivalent of negative 2 times 5 times x. So because it's all multiplication, the order of multiplication doesn't impact our result, and we can associate the multiplication in ways that make it more convenient. So in this case, for instance, the problem started out with 5 and x being associated because they were in parentheses. So the 5 times x was the thing that was kind of being prioritized. But when you multiply 5 times x, all you get is 5x because one's a constant, a number, and the other's a variable, a letter. And so when we multiply them together, putting them next to each other, saying 5 times x is the best we can do until we know what x is worth. Now, compare that to multiplying negative 2 times 5. Negative 2 times 5 is negative 10. And so if you were to associate negative 2 and 5, then you could actually simplify. You could actually do the multiplication, and that's what we want to do. So negative 2 times 5 is negative 10x. And so that's the answer. That's the simplified version of the original problem. And I hope it makes sense that whenever we can, what we want to do is multiply and combine our numbers. And then, of course, later on, we'll do the same thing with any variables. We'll put those together too. So we can, in addition to the associative property of multiplication, we can use the associative property of addition in the same way. So if you look at this problem essentially says 2x plus 5 plus 10. So it kind of says 2x plus 5 plus 10. So since it's all addition, the parentheses here were showing us what to do first, but what we do first won't impact the final result because it's all addition. And so we can actually associate the operations together that might produce a more simplified answer. So for instance here, instead of thinking about 2x plus 5 as the thing that needs to go together, I should probably be thinking about 5 plus 10 as the thing that needs to go together. So 2x is not a like term with anyone else. It doesn't have anyone else to mix with. But 5 and 10 can add together to get 15. Now, in addition to the associative property, we also have the distributive property. And the distributive property is really helpful because let's take a look at something like this. Let's look at, how about 3 times 4 plus 1. Oops, excuse me. 4 plus 1. 3 times 4 plus 1. So what we would do if we're asked to simplify, then what we would do is we'd want to do the work inside parentheses first. 4 plus 1 is 5. And then multiplication is the only thing left, so 3 times 5 is 15. So 15 is the simplified version of this. Now, what's interesting, though, is that I don't have to simplify inside the parentheses in order to get the right answer. If I distribute, So what this says is 3 times 4 plus 1. So if you're not going to add 4 plus 1 before you do the multiplication, then what you have to do is you have to distribute the 3, the multiplier, to all the terms inside parentheses. So instead of looking at this as 3 times 4 plus 1, it's going to be 3 times 4. So I multiply the 3 times the 4, plus then I multiply the 3 times the 1. So if I triple the whole thing, that's the same as tripling all the parts inside. But I have to do it to all the parts inside. So now I can keep simplifying. 3 times 4 is 12. 3 times 1 is 3. And 12 and 3 make 15. So sure enough, it checks out. It works. The distributive property works. And so what I want to do now is I want to use it when it's not all numbers and I can't combine things. So for instance, look at that 3x plus 5 inside parentheses. So 3x is a variable term. I don't know what x is actually representing yet. And 5 is a constant term. It's always worth 5. So I can't add them together any more than I've done here. But I want to do this multiplication. So what I'll do is I will distribute my 4 to the parts inside. And I should be really specific. It's not 4. It's negative 4. And that's really important. So it's negative 4 times 3x plus negative 4 times 5. So I distribute the negative 4 and I multiply it to each part. Now I'm going to simplify. Negative 4 times 3x is negative 12x. Negative 4 times 5 is negative 20. And then to add a negative is the same as subtracting. So instead of adding a negative, I'll just subtract 20. And so that is the simplified version of that. So even though I couldn't add 3x plus 5, didn't mean I couldn't distribute and simplify some. So here's table 1. You can see is just a list of different ways to think about the distributive property applying. And let's look at this example here. 2 times 3y plus 4 plus 5. So my goal is to combine all the terms that I can. In this case, I see that I do have some constant terms, some numbers on their own, and so I want to add them. Unfortunately, 4 is inside the parentheses, 5 is outside the parentheses, so to get 4 outside the parentheses, to add it with 5, I have to do whatever operation is in front of the parentheses. In this case, it's multiplied by 2. So I have to double everything inside parentheses in order to do the multiplication. So I'll go ahead and distribute 2 times 3y plus 2 times 4. And now this plus 5 is still hanging out on the back end. So instead of 2 times 3y plus 4, it's 2 times 3y plus 2 times 4. So I'm doubling each part. Now I can go ahead and do the math. 2 times 3y is 6y. 2 times 4 is 8. And so then 6y plus 13 is a simplified version of what we started with. Now we call this distributing across the terms, or distributing across the sum. In this case, they say distribute across the sum. But the distribution property is pretty powerful, and we're going to be using it a lot. So practicing multiplying through parentheses, distributing whatever multiplier is in front, the factor in front, to all the terms inside. Very important. Let's do another problem here that has us sort of combining all of our skills. You know, we have to use the distributive property a couple of times. We have to follow the order of operations. We have to combine like terms. So we will go ahead and distribute. So this is 2 times 3x plus 2 times 1 plus 4 times 2x minus 4 times 5. Now, notice I wrote this plus here, and because it's positive, you know I don't have to write a sign, except that here it was a minus 5. So a positive 4 times a minus 5 is going to be a negative 20 at some point. And so instead of putting plus 4 times negative 5, right, which didn't seem to make as much sense, I simply wrote this sign here, and then I multiplied the 4 and the 5, and I know that it will resolve in the end. So I'm going to go ahead and get rid of some of those confusing arrows. We'll just focus on this main one here. So now I can find all my subproducts. I can do the multiplication parts. So 2 times 3x, 6x, plus 2 times 1 is 2, plus 4 times 2x is 8x, minus 4 times 5, so minus 20. Now what I want to do is find my like terms. So I have 6x and 8x, they could go together because they're both x terms. And then I have plus 2 and minus 20, and they could go together because they're both constant number terms. And so what I'll do is I can rewrite them using the commutative property. I can rewrite them next to each other if it helps me to see. And so here, 6x plus 8x is 14x. And then plus 2 minus 20. If I have $2 and I try to spend 20, then I'm short $18. So this is the simplified version of what we started with. And we were able to obtain it by distributing through the parentheses to all the terms inside and then combining like terms. Okay, there are a couple of geometry problems, and so we're really quickly going to talk about some basic geometry. We're interested in finding the perimeter of an object, and so let's talk about the square. So a square has a side S, right? S for side. And what we know is that in a square, all 4 sides are the same. So if you want to find the perimeter, right, the distance around, the perimeter, the distance around the shape is all 4 of these sides added up. So you could say S plus S plus S plus S, or what we typically prefer to say is 4S, 4 sides. So if you know one of the sides of a square, you can find all 4 sides, the entire perimeter of the shape, by multiplying by 4, because all 4 sides are the same. Now compare that to a rectangle. Rectangle means right angle. So all it means is that there's a right angle here, and we know that there's 2 sides that are shorter, that are the same. So we'll call these maybe the width. And then there's two longer sides. And we'll call these L. And so if we want to find the perimeter of the shape the whole way around, we could start by adding the 2 W's, the 2 widths, and then we could add the 2 lengths. Or a simplified version of this, we'll say, oh, that's 2 W's plus 2 L's. That's 2 lengths plus 2 widths. So if you knew just one width and one length, one of the right angle lengths, then you would know what the entire perimeter of the rectangle is. Now let's look at triangles. Triangles can come in all sorts of shapes, right? A triangle simply means three sides, right? So it can look like this, where it's a right angle triangle, right? And they meet at a nice right angle, sort of like part of a rectangle or square. You could also have, you can have an isosceles triangle, where two of the sides are the same. Or you can have an equilateral triangle, where all the sides are the same. And you can have a bunch of different ones in between. And so the important part to remember is that the perimeter of a triangle is simply all the sides added up. So if you have 1, 2, and 3, you can add them up and you'll get the perimeter. And there's not usually a simpler way to think about perimeter of a triangle. Now let's compare that to a parallelogram. Parallel, meaning going in the same direction, right? Not intersecting. Parallel, sort of like the two L's right here in parallel lines, like railroad tracks. And then gram, just meaning a shape. So this is a shape with parallel lines. And so in the case of the book, problem they're going to give you looks a little bit like this. And if they want to know the perimeter, well, what you know is that this side here, much like a rectangle, this is actually like a rectangle that's just been tipped over a bit. But you could imagine if you have a shed and the walls are kind of weak and you tip the whole thing over, but it doesn't collapse, well, each wall is leaning at the same angle, right? And so each wall is still the same length, leaning at the same angle. It's just that the roof is no longer straight up and down over the foundation. So that's what's gone on here. So here's a side. We'll call this, we'll go ahead and call this a width. And we'll go ahead and call these lengths. And so the parallelogram, to find the perimeter, is a lot like a rectangle, actually, because you still have two of the same widths and two of the same lengths. And so what we can do is actually follow the same basic formula, and we can have two widths plus two lengths, and that will find our perimeter, our way around the whole parallelogram. So hopefully those tips help you with those handful of geometry problems at the end of the section. So let's review some of the key concepts here. So what property allows 5x plus, 5 times the quantity, 5, here's a, 5 times the quantity, x plus 3. What allows that to be written as 5x plus 5 times 3? The distributive property is what allows us to do this. The distributive property. And the distributive property applies to whenever we're multiplying and we have multiple terms inside parentheses. We could be adding or subtracting inside the parentheses, but we have a multiplier out front and we need to multiply terms inside that aren't like, and we can use the distributive property. Let's go into B. Why is simplifying an algebraic expression using like terms important? Well, if you didn't simplify using like terms, then it wouldn't be simplest. And in fact, we know that say you're organizing your closet. What you'll often do if you want to get really organized is you might put all your shirts together, you might put all your pants together, and you might put all your heavier items like your coats together. And you do that because they're all like items. They all look a little different, but you know they're all in the same category. And so going together makes things simpler. And so that's the same idea that we take in algebra, is that we always want to simplify as much as possible, so that if I have something like 3x plus 5x plus 2, a simpler way to write this is 8x plus 2. And so whenever possible, I want to combine like terms, because that will help me have the simplest expression possible. Okay, C. What does it mean to find the value of an algebraic expression? Well, what it means to find the value of an algebraic expression means to substitute a known value and either evaluate is usually the word we evaluate, or you might see simplify. Simplify and evaluate when it comes to reducing algebraic expressions to their simplest form. Evaluate and simplify sort of are interchangeable. And so substitute a known value, the one they usually give you. They'll say something like, the expression is 3x plus 5, 4x equals 4. And what you do is you substitute the known value, and then you can evaluate or simplify the algebraic expression. Notice we don't solve expressions. We simplify, evaluate, or find the value of algebraic expressions. We'll save the word solve only for equations that are given to us as equations. And you'll see what we mean in the next section. All right, part D. What is the difference between a complementary angle and a supplementary angle? Well, don't worry about this part because we didn't cover it. But if you want to know about it, you can check out your book. It's got some pretty good diagrams. Basically, what it has to do with is that if you have a 90-degree angle and you draw a line from the point where they meet, then and you bisect this area, then you have some portions, A and B, that complement each other up to 90 degrees, right? They are each other's complement. Then you have another idea that if you have a straight line, 180 degrees, and you do the same thing, draw a line from that horizontal line, that you could create two different angles here and here, and that those angles, they sum to 180 degrees, because right angles are 90 degrees, and straight lines, turnarounds, are 180 degrees. So don't worry too much about this one for now, because it's not really a part of our homework set, but that's what they're talking about when they talk about complementary and supplementary angles. And if you're going into a field that involves geometry at all, anything hands-on, then that'll definitely come in handy for you. So hopefully that answered some questions you had in 3.1, and if you have more questions, don't hesitate to reach out to me, be in touch, make an appointment, or send a message, and we'll connect, and I'll see you in 3.2.